K, the equilibrium constant. What is K? You should know that K is a ratio, simply a ratio of the concentration of products over to the concentration of reactants. If you have a large K, you have more products. If you have a small K, you have more reactants. Now, how does this apply? Well, what we're going to do is look at some situations where the reaction system is actually not at equilibrium. And we don't call that K, we have a different letter for that. So we call that Q. Q is the reaction quotient. Now, how do you calculate that? Well, exactly the same way. Q is equal to the concentration of products over the concentration of reactants. Now you ask yourself, why is Q valuable? Well, Q will tell us how a reaction will change in order to achieve equilibrium. Remember, at equilibrium, the rate of the forward is equal to the rate of the reverse, and that is what is equal to those two rates. The reaction quotient, a couple things about it. To calculate Q, one substitutes, usually it's the initial concentrations of the reactants in the products into the equilibrium expression. Q gives the same ratio, exactly the same ratio as the equilibrium expression, but for a system at any point. It does not have to be at equilibrium. But usually also specify the conditions such as temperature, because we know K changes with temperature. So let's look at a couple situations. Let's say Q is equal to K. Well, Q and K are equal. That system is at equilibrium, because we know K is equal to the concentration of products of reactants, and Q is actually, if we were to say this was Q instead, if we were to say Q, we would just substitute Q here and say Q is equal to those. But if we were to do that calculation for Q and find that it's exactly the same as K, that means that system is at equilibrium. The amounts of products and the amounts of reactants we have are exactly the same as we would have it as if it was equilibrium. Now, one thing to think about when we talk about this, we're saying things are equal. It doesn't mean the amount of reactants and products are equal. It means that Q and K are equal. Now, let's look at another situation. Q is greater than K. Now, if you remember back to our formula, remember Q is products over reactants. So if Q is too big, it means we've got too many products. Now, how do you get rid of products? By going in reverse. By going in reverse, we say it shifts to the left. So two important things here is when Q is greater than K, it shifts to the left. So here we have a Q that's greater than K, and we see that it's shifting to the left to achieve a position where Q and K are equal. So that's when Q is greater than K. Let's look at the opposite situation, where Q is less than K. So we see we have here a small Q, and it's not equal to the K, so Q is smaller than K. In this situation, it's going to shift to the right. Now let's think about why. Remember, Q is products over reactants. If Q is really small, it means we're dividing by a much bigger number. So that means we have more reactants than we need. The only way to get rid of those reactants is increasing the forward rate of the reaction. When you increase the forward rate of the reaction, more products are produced and more reactants are consumed. As you have more and more products and fewer reactants, Q will become bigger and bigger until the point where Q and K are equal. And at that point, the two rates will become the same and it has reached equilibrium. So how do you remember all this? One way I think about it is in the number line. So on the number line, I think of K right in the center. So what happens? Remember using Q is equal to products over reactants. So if Q and K are equal, they're exactly the same position on the number line. So there's no reason, there is no shift. It doesn't go right, it doesn't go left, it's already where it's supposed to be. Let's look at some other situations. Let's say Q is greater than K. When Q is greater than K, remember we want to have fewer products and more reactants. So anytime Q is greater, so we see Q here on the number line being greater, that means we're going to shift to the left. So if it's too big, you want to get to where the K is, so you want to shift to the left. So there we see it shifting to the left. Let's look at the other situation. We see here when Q is smaller than K. When Q is smaller than K, we want to get to the position where K is. So in this situation, we're going to shift to the right. So Q is smaller than K, the shift goes to the right. Then finally, we have the situation where Q and K are equal, and that's one I mentioned at the very beginning. In this one, there is no shift because it is already at equilibrium. So how does this work when we do problems? Let's do our first problem here. This is an example we have at 448 degrees Celsius. The equilibrium constant, or Kc, for the reaction below is 51. I'm going to show you the reaction in just a second. Now, here's a reaction. Hydrogen gas plus iodine gas produces 2 hydrogen iodide. Predict how the reaction will proceed to reach equilibrium at 448 degrees Celsius if we start with 2.0 times 10 to the minus second moles of hydrogen iodide, 1.0 times 10 to the minus second moles of hydrogen gas, and 3.0 times 10 to the minus second moles, that should be moles, of iodine in a 2.0 liter container. So the first thing, like we do with all these problems, is we see the equilibrium expression written. Next, we want to write, instead of a Q expression, a K expression. It will look exactly the same. We'd say Q is equal to products over reactants. So for this one, it would be Q is equal to the concentration, remember brackets are concentration, of hydrogen iodide divided by the concentration of iodide times the concentration of hydrogen. Now we simply need to insert the values. Now before we do this, notice these are not molarities. All of these are in a 2-liter container. So that means we need to take, for hydrogen iodide, and divide this by 2. And hydrogen, and divide that by 2. And then the 3.0 times 10 to the minus second, this is moles of iodine, and also divide that by 2. When we do that, insert those values, this is what we come up with. 2.0 times 10 to the minus second divided by 2 gives you 0.01, and that's going to be squared. And then we have the 3.0 times 10 to the minus second for the iodine, and that should be the 0.015. And then for the 1.0 times 10 to the minus second moles of hydrogen, we divide that by 2. That should give us 0.005. So we have these values and we solve for them. Find that Q is equal to 1.33. If you refer back to the problem, we see that Q is actually less than K, because we found 1.33, which is less than the K, known to be 51. Thus, the system is not at equilibrium. Now, what is it going to do to achieve equilibrium? Which way should it shift? That's the other part of this question. So if Q is less than K, remember it's to the one side of the number line, it's going to shift to the right. So the reaction will shift to the right to produce more products and to also use up more reactants. So you're going to have a bigger number in the numerator, and the denominator is going to be, you're divided by a smaller number. So in the process, the concentration of hydrogen iodide must increase, and the concentration of hydrogen and iodine both must go down. So this is a good example of a Q problem. There's many more that we're going to work on. Just let me know if you have any questions, and I'll see you tomorrow in class.